Okay, yeah, I'm working with Danny, Ben, and Deyu on Gaussian process and deep Gaussian process and some of the Bayesian statistics right now. And today I'm going to talk about Vecchia Approximation, deep Gaussian processes, and an amazing phenomenon that I found during implement Vecchia Approximation inside of deep Gaussian processes model. Yeah, here we go. So at the beginning, I would like to give a brief introduction about the Gaussian process model. So imagine that you have several locations, S1 to Sn, and each of the location you have a corresponding scalar output y here. And you can collect all the y together into a column vector. And instead of define a distribution over a fixed number of variables, you define in Gaussian process, you define a distribution over functions. And so you can think of it as a collection of random variables. So you now view the Gaussian process as a generalization of multivariate normal distribution, and each of the y element here follows a univariate normal distribution. And as you can see in this formula, the Gaussian process is characterized by a mean vector here, mx, and a covariance matrix k. And inside of the covariance matrix, there exist kernel functions to quantify the relationship between any two locations in a dataset. And there are several kernel functions that you can choose, like square exponential kernels or Martin kernels, which is the most popular one. And inside of the kernel functions, there are several parameters that we want to estimate during the training process of the Gaussian process model. So, but there exists a big drawback for the Gaussian process model, because Gaussian process model, the kernel function inside it has relatively simple similarity matrix, but regarding to some specific data sets or specific problems that we want to use different similarity matrix at different region of the input space. So for this example, this is wiggling here, and this is really smooth here. So we want to use different similarity matrix. So that's why we are using a hierarchical structure for feature extraction. So that's why we come up with the deep Gaussian process model. So in the last few months, I have been working on to reproduce a Gaussian process model from scratch on my own. And so I following this paper, Active Learning for a Deep Gaussian Process Surrogates from these guys. And the reason why I'm not coding up the DGP SI from scratch, because it is too hard. This paper is more straightforward, so I can code it up in like few weeks and make it working. But DGP SI, yeah, I still have 3-4 years, so yeah, maybe in the future. So according to their paper, I reproduced the deep Gaussian process model. As you can see this graph. This is one of the simplest version of deep Gaussian process model. And as you can see that this is the input X, and they pass it through to several GP models here. And each of the GP models have their own parameters, theta W1 to theta WP. And then it come up with several like latent values, W1 to WP, and then it all pass to the second layer. In this two-layer case, we call it out layer. And here, as you can see here in their paper, they just set the second layer to have only one Gaussian process model, and then it come up with the output Y in the end. And that's the formula for it. Yeah, this is a little disgusting. Doesn't look that charming. This is in their paper, they have like a deep sampling procedure for this two-layer deep Gaussian process model training plot. And actually they're just using like the most classic MCMC method for sampling the parameters for both layers, and using the elliptical size sampling for sampling the latent values. So yeah, as soon as I finish reproduce the deep Gaussian process, I'm suddenly aware of a problem that make a lot of GP and DGP researcher miserable is the computational bottlenecks in the deep Gaussian process model. And as you can see, this is the log likelihood of a Gaussian process model. Like every time you do an evaluation of this log likelihood, which involves the matrix inversion computation here, this sigma n, and each time you do this, and this one typically relies on the Cholesky decomposition of the covariant matrix sigma n. And this operation generally requires n squared memory and performing n cubed floating point operations to obtain the Cholesky factor of this matrix, and both of which are computationally prohibitive if you have a really huge data or the data sets that have really high dimension. So there are a lot of attempts to solve this problem, and one of which is called Vecchia Approximation. It's from Vecchia in 1988, I guess. And this like in the background of any joint distribution can be factored into a product of conditionals like that, Py equals to Py1 and Py2 given y1, all the way to Pyn given yn minus 1 till y1. Remember this? This is really, really important. And the key idea was simple: to approximate the joint distribution by considering only a subset of the neighboring points. So in this formula, for the yn case, you only have to consider a subset within the yn minus 1 to y1. And for the y3 case, the only choice you have is y2 and y1. So this approximation leads to a highly sparse Cholesky factor of the precision matrix. Precision matrix is just the inverse of the correlation matrix. So as you can see, it's here. And Mathis Kaspers and Joseph Grenis in their paper, A General Framework for Vecchia Approximation of GP, they derived a closed form solution for populating UW, which is the Cholesky decomposition of the precision matrix. As you can see here, now we only have to do a much smaller matrix inversion computation. So right now it's the subset you're choosing for each of the locations. So if I choosing a m which is much smaller than the original data set, so right now you turn the original n cube operations to n times m cube operations. So this is a huge improvement regarding to the computation in Deep Gaussian process. So, but there's still several choices that you have to make before you are doing Vecchia. The first one is the ordering of the data. So why ordering of the data matters? So remember in this formula that for example, we have the data number of 100. So this is 100, and he can choose from point number one to point number 99. But for number 3, you only can choose number 1 and number 2. So who's going to be the 100? So who's going to be the 3? That's quite important. So, but there are several choices for data ordering, like random ordering, which is the most commonly used one, and a lot of papers have shown it presents a really good result. And it's also used in the package of DGPSI, and also Kaspers, the author, also get a maximum minimum ordering working in the Vecchia, and it presents a better result than the random ordering, but it suffers from some of the computation burden problems. And the number 2 choices that you have to make is the number of neighbors to be conditional. And it's quite obvious that the more neighbors you are choosing, the slower the computation will be. But and you also imagine that maybe the more neighbor I'm choosing, maybe the prediction accuracy will increase, but that's not the case. So after I test it, it doesn't matter how much neighbors you are choosing, whether it's 2 or 50, 54, 100, it doesn't matter. It don't have like a really good, really big difference. So that's one of the problems I'm looking at in the future. Yeah, and here is a simple example of random ordering and nearest neighbor. And as you can see here, all the black dots are, and now we set the number of neighbors to 30, and all the black dots are ordered from 1 to 50. And the circled one here is the number 50 points. So other than that is number from 1 to 49. And the square points here are the 30 nearest neighbors to point 50 among these 49 points. And the right one is the same, but it's for number 330. That guy. And the other is the same. And as we can see here, like at the beginning of the order, the neighbor you are choosing is more sparse in the space, but as the order goes high, the nearest neighbors is getting closer and closer. And so now we implement Vecchia inside of the Deep Gaussian process model, which is quite simple. We just impose the Vecchia approximation at each layer of the Deep Gaussian process using the sparsity of the upper-lower velocity decomposition of the precision matrix. Then the two-layer Vecchia DGP model would just look like that. Yeah, you don't have to. And regarding to the ordering and the conditional set, each of the Gaussian components of the Deep Gaussian process could have its own ordering and conditional set. For example, we can set like layer 1 to have 10 nearest neighbors and layer 2 have 5 nearest neighbors. It doesn't matter. And according to CASFS, we update the ordering and conditioning separately given the current estimate of the parameter, but only at certain iterations like 2, 4, 16 to avoid slowing the algorithm unnecessarily. Yeah, so now we have DGP working, and now we have DGP implemented with Vecchia approximation. So now I want to test how good it is, like its speed and its accuracy. How much accuracy would I lose if I using this approximation method? But it is really fast, obviously. But and the common sense tells us when you make an approximation to a statistical model, you will sacrifice something. You will sacrifice accuracy for speed, or you sacrifice speed for accuracy. But after I test my code, each time, most of the time when I do DGP using Vecchia, regarding to the prediction result RMSE, sometimes it performs better than not using the Vecchia approximation. And I was shocking. I said there's something wrong in my code. So I test the Deep GP package from the soil, and they have the same phenomenon as well. And then I test DGPSI, they have the same phenomenon. So I was shocking. But the thing is this phenomenon is not consistent. Sometimes DGP performs better, but sometimes DGP using Vecchia performs better. So I want to test more. Yeah, test more. And it shows like this. This is RMSE result after 1000 training and prediction using the DGPSI. As we can tell here, the mean RMSE for this 1000 experiment shows that using Vecchia performs better than not using Vecchia. Amazing, right? So after I talked to Danny, there are several speculations on this phenomenon. The first one is it is possible that in some random orderings, the nearest neighbor of the points in areas with very large variations, like area 1, was chosen more closely to make the model more sensitive to changes in values, while fewer points was selected in smooth areas, like area 2. And the second one is every time when you are doing a matrix inversion, it will cause some numerical errors. And maybe when you're doing Vecchia, so you're making the matrix become much smaller than the original one. So the numerical error reduction just covered the information loss when you do the approximation. And regarding to the future work, so I will still want to test whether this phenomenon exists in the high-dimensional data, and to build a model. And second one is to build a model to quantify the probability of choosing the closely nearest neighbors. And the third one is try to find a better ordering algorithm or derive an algorithm to search for the optimal number of nearest neighbors. Thank you. Oh, sorry.